Closing off an exciting sequence of talks in theory, we have our save the best for last. We have our the last opportunity to see a TTI. I think it's right. You'll probably last talk at TTI. Closing talk. Yeah. So all the tickets are sold out for Siddharth. Siddharth's talk. Siddharth has been here for about 2.5 years. Working on differentiation algorithms, and is going to be headed to Amazon in a few weeks. So if you have some book orders, you can start placing them. But I'm sure they'll be continuing, other than sending us books, continuing to do interesting things also there. Okay.
Thanks, Nari. Thanks so much. I had a wonderful time till now. And I hope that continues after the talk as well. So I'm going to be speaking about an interesting setting that comes up in legal e-discovery. And this is based on joint work with Liren, who is in the audience. So all questions should be directed to Liren. And with that said, let me begin by what is perhaps the best way to begin a talk, by apologizing. I'm not an expert in any legal matters or other matters for that instance, but I'm going to try to distill and present some abstract framework which tries to capture the issues that arise in legal suit. Okay. So, yeah, you shouldn't like sort of base your legal suits on what you're hearing in this talk. It's not going to be pretty far. But let's assume that Bob somehow is unhappy with Alice and he's filed a legal suit against Alice. And Bob is a plaintiff and Alice is a defendant. And let's just, for example, suppose that Bob says that Alice has given unfair pricing to Bob for some goods, right? And Bob can then request a production of relevant documents from Alice. So these could be, like bills that Alice has about her interactions with other customers. It could be various things depending on what the lawsuit requires. So Alice holds, when I say that Bob issues a request for production, it's Bob's legal team asking Alice's legal team for whatever relevant documents Alice might possess. So she holds a lot of documents, some of which are relevant, some of which are not. And so these relevant documents are what we are going to call as responsive documents. And some which are not relevant are the non-responsive ones. And Alice is concerned about the privacy of her documents, right? She doesn't want to reveal unnecessary documents because that might contain sensitive information. On the other hand, she also has an incentive to hide some responsive documents if she fears that could, lead her into trouble. So there is a kind of tension here that Bob wants to learn all the responsive documents, but Alice wants to not reveal non-responsive documents, and perhaps if you just trust Alice blindly, she would even hide some responsive documents. Right? So what is currently done in such a situation? So the entire burden is kind of placed on Alice's legal team, that they are supposed to operate ethically under professional guidelines to reveal whatever documents are relevant to the litigation. Right? But there are many issues with such a setting. So first is accountability. I mean, you have to sort of assume that Alice's team would follow the legal standards when they review. There is also the transparency issue that Bob has no way of being certain whether all documents that were relevant to their situation have been revealed. And there is also a misalignment of incentives for Alice's legal team, right? Because they are asked to conduct professional responsibility which is not benefiting their employer. And it's also expensive. Like if you imagine these documents are like some digital documents, digital invoices, this requires a lot of manual effort, and in fact it has led to some frivolous lawsuits just because they know that costs a lot of money to do, right? And furthermore, even if you assume that nobody is malicious, these are kind of prone to unintentional errors. So the other extreme could have been that you just disclose everything that Alice has to Bob, but that will cause significant privacy loss. And yet another situation could be that you just submit everything to the court and then the court decides which are relevant and which aren't. But that is too expensive because the court doesn't have such time to adjudicate on every document. So there is a new sort of paradigm that's come in. It's not new by ML standards, perhaps new by theory standards, since I think it's probably 2 decades old. So where they are using these technologically assisted learners to basically pick out the relevant documents that Alice has. Okay, so the idea here is that this would reduce the manual effort on that has to be performed by Alice's legal team. And there have been interesting cases, not that I know too much about them, where this kind of tools have been used to discover the relevant documents, although the courts have explicitly said that it's not mandatory to use them, but you may use them. The Alice's legal team may use such tools to discover relevant documents. And the problem with this technology is still accountability, that nobody really knows what Alice's legal team is up to. Are they really hiding documents or not? Because the entire process is shipped to them. Yes?
So the issue here is that we don't know that they're actually running the program they said they're running, or is the issue that we don't know what the program is doing?
So both. Even if you tell the process, go train a classifier and on some documents, like just a usual ERM protocol, and then label the, do random sampling, manually label the documents, run a classifier, etc., etc. It's not clear what Alice's legal team is doing. And second, even if they are following the true protocol, it's not clear whether all the documents were fed to the protocol.
You assume that the concept of a relevant document is well defined. It's binary classification. Yeah.
Yes, that's a very good point. And for now, we are going to assume it's well defined. If there are conflicts, we will see later. If there are conflicts between Alice and Bob as to the relevance, we will use the codes to resolve that.
But for now, it's binary classification.
It's binary classification. So this the accountability issue is really what is the bottleneck with this kind of learning theory-based approach, or learning the responsive from the non-responsive documents.
So this TAR, it's not a completely automated process in the sense that in this TAR, first Alice's team has to actually train the model. So it's on them to train the model and then run it. It's not that it's completely automated.
Yes, and I'll get to that in the next slide. You're right.
Yeah,
That's
okay.
how it
I was
is.
just trying to,
Yeah, that's the reason why, because there is a part where Alice's legal team can do stuff which is not supposed to be done. So there was, a paradigm introduced by Cormack and Grossman, where they introduced this framework of continuous active learning, which kind of does what Nati is saying. Their idea was to reduce the manual effort. Their idea was not to address this issue of privacy versus discovery of all relevant documents. But let's just look at what it does in a very short way. So it takes all the documents, it kind of thinks of them as high dimensional vectors, and it starts training an SVM on them. Initially it gets some labeled data, it tries to learn some classifier, and then it scores the remaining unlabeled documents, picks the one which are most likely to be relevant, and it asks Alice's legal team to review those documents. So manually label the most relevant N documents, and then repeat this procedure iteratively until you've gone over all the documents. And the issue here is that again it requires manual review, so it doesn't get rid of this accountability concern. And that is one of the things that was pointed out here, that seems to be a big bottleneck to adopt this technology. Okay, so what do we want now that we have somewhat laid the paper? What do we exactly want? So this problem was formalized into a multi-party verification task by Dong, Hartline, and Vijay Raghavan. And they sort of laid out what we should look for. So we want to design a protocol which has the following properties, roughly speaking. Yeah, so this is, I'm sort of defining everything informally, but it's not too difficult to formalize all this. So we want recall. So we want to say that a high fraction of responsive documents are learned by Bob once the protocol is learned. This is not contingent on Alice's behavior. Alice can try to hide critical documents which might incriminate her, right? But despite that, we should have high recall. And then the privacy part is captured by the non-responsive disclosure. So assuming that Alice acts truthfully, that she reveals all the relevant documents she has, her privacy should not be leaked, that there should be minimal non-responsive disclosure. So of the non-responsive documents that she holds, as few as possible are revealed to Bob. So these are the natural two parameters which are in tension with each other. And of course, I mean, eventually you want things to run efficiently, at least empirically. And a minor thing is also, it would be good if Alice's dominant strategy in this protocol is to be truthful. But for this talk, let's just focus on the first two points. That is, we want high recall and we want low non-responsive disclosure. Yes.
Dominance with respect to what measure? The second one, I presume. She wants to reveal as little as possible what she's not supposed to reveal.
Yes, that's So let's try to set up the protocol somewhat more formally. So we are going to think of Alice's documents as some points in RD, and they can be partitioned into truly responsive documents and non-responsive ones. So this is the ground truth. And both Alice and Bob, we are assuming, can determine the responsiveness of a document. Like, if there is a conflict, we will use the courts to adjudicate, but we'll see that in a bit. And we'll also assume that there is a known hypothesis class H, which accurately classifies document responsiveness. So this, Alice and Bob might agree that there is a kernel-based classifier which works, or there is a more complicated neural network which does this. But this is known, like both agree that there is some hypothesis class which will be rich enough to capture responsiveness and non-responsiveness. And we don't assume that the instance, so by instance I mean the way S is being partitioned, it's realizable with respect to hypothesis, with respect to the hypothesis class. It can be non-realizable, but it should at least be somewhat accurate. And so in the original paper, Dong, Hardline, and Vijayaraghavan, they argue that it's good to assume there is a trusted third party because a lot of these documents are anyways stored electronically, not on the company's server. They are with a third party anyways. So the third party has all those documents. And if this is like a big email server or like a host company which can be trusted, then they can run some protocols on behalf of the code, which is somewhat more appealing than just pushing all the burden on Alice's legal team because they are incentivized to work for Alice. And we will assume this, that Trent receives all the documents from Alice. So it's kind of like they are already there, but you can also imagine that Alice will supply every document to Trent. So here it's sort of more difficult to get plausible deniability. Earlier she could have said, I didn't think this is relevant, but it's more difficult to justify why you did not submit all the documents rather than why you did not submit all the relevant documents. Okay. And she will also send to Trent the alleged responsive documents. That is, what are the documents she thinks are responsive. This can be either done by manual review or this can be done by just running the technology assisted review on her set. Now, Trent can't really determine the labels because Trent is not an expert in legal matters, but they can perform computations. And Trent can coordinate with Alice and Bob over the labels of documents. Like if Trent wants to figure out the label, he can ask Alice or Bob what should be the label of this document. And if there are conflicts, they can also consult the code. Right? But consulting the code is considered very expensive and you generally want to avoid that. You don't want to consult the code on every document. So this is the setting of our protocol. We are trying to develop a protocol where we have these resources, we have this trusted third party, and we get high recall and low non-responsiveness. So let's look at a very toy protocol just to whet our appetite. So let's assume that.
Sorry, just a second. So if I'm still correct, the model here is that both Alice and Bob actually agree on what's internally, they agree on what's relevant and what's not relevant. And the only reason to dispute the court is if one of them is going to not be truthful, or do they actually sometimes truly disagree?
So for now, so we deal with both cases. It is going to happen that Alice will inadvertently make mistakes. So we are able to take care of both cases. That even if they are trying to be malicious, the protocols are designed assuming that they are malicious. But the non-realizable setting sort of for free gives you the other concern that you had. That even if they make a mistake by not knowing, or they did not really think, genuinely did not think it's relevant, it will be taken care of in the final recall and non-responsive guarantees that you give. So let's just for example take the situation where the data is one-dimensional. So all of Alice's data are just really lying on the line, and let's also assume that it's kind of linearly separable. It's a very simple case. So there is a threshold which separates the non-responsive documents S minus from the responsive ones. So this is the ground truth. And what happens in our protocol? The LS labels from Alice are sent to Trent. So the picture at the bottom is what Alice sends to Trent. So she sends all the labels as they are except for the label of point P, which she's trying to hide. Okay. But first off, because it's a toy example, let's just assume that she will at least send a partition which is linearly separable, because if it isn't, Trent can just object at that stage itself. Now, this A plus is what she has alleged are the total relevant documents. Okay. So what will Trent do at this point? So Trent will compute this critical point P, which is actually just the closest point to the boundaries, the closest point to the threshold, which is negative. And Trent will just verify the label of this point P with Bob. Trent will send this point to Bob and ask whether it's actually relevant or not. And if there is a conflict on the label, that is, if Bob says it's relevant, but Alice is claiming it's not relevant, then we will just use the code to adjudicate and figure out what's happening. Now, if we realize that this document is truly relevant, then the protocol stops. We do nothing. So Bob has learned in this case A plus and P. So yeah, if Bob classifies P as non-responsive, we reveal A plus to Bob and the point P. And otherwise, Trent just reveals all the documents to us. So in case Trent finds that Alice was trying to cheat, they will just reveal all the documents to Bob. Okay. This is like a all or nothing game here. So let's just make sure we understand what the recall and non-responsive disclosure are for this protocol. So the recall is 1. In either case, we are guaranteed to learn S plus. If Alice behaves truthfully, then A plus is indeed revealed to Bob, which is S plus. And in this situation, the entirety of the data set will be revealed to Bob. So in both cases, we see that the recall is 1. And what about the non-responsive disclosure? So if Alice acts truthfully, she supplies the correct set A plus as S plus, there will be at most one critical point that Trent will be sending to Bob for verification. So in this simple setting, the non-responsive disclosure is 1 and the recall is also 1. Okay. So let's see what the prior work in these kind of frameworks are. So as I already said, this framework was defined by Dong, Hartline, and Vijayaraghavan. And they established this question, and they also gave a protocol which works assuming that your data is linearly separable in RD. It kind of borrows this critical points framework, but there is a little more intricacy that is required with higher dimensions. And as you can see that in this situation, the data is linearly separable in R2, and then this highlighted red point will be a critical point because it's closest to the boundary. Their protocol achieves a recall of 1, and because they have a little more intricate revealing mechanism for the non-responsive disclosures, they are actually able to show that their protocol is kind of instance optimal. That is, amongst all protocols that have a recall of 1, theirs achieves the lowest minimum possible, the lowest possible non-responsive disclosure.
So about the previous protocol, I'm a bit lost. What is the incentive for Bob to behave truthfully? Why he does not say that I don't admit and get everything?
Oh no, because if there is a disagreement, trying to use the code to figure out what is the true label.
So he will get everything only if it was Alice who had lied.
Yes.
Okay.
Yes.
So actually what happens here in the almost the last bullet is it's not otherwise Trent reveals all the documents, but otherwise Trent goes to the court, and if the court decides that it was relevant, then it reveals all the documents.
Oh right, you're right. Sorry, I should have said it. I'm sorry, yeah. They check with the court before. Yes, you're right. Thank you. So as I said, there was this original paper which started this question, and they gave a critical points protocol when the data is perfectly separable by a linear classifier. And then they also give a TAR scheme based on this protocol, which works as long as the learning algorithm satisfy a certain hypothesis. So for instance, it wouldn't work if you were using something like a perceptron learning algorithm, but it works with SVMs. There's a certain hypothesis they need in which they can actually make this technology assisted review scheme have the recall and non-responsive disclosure property.
So I'm a bit confused. So what, for a linear classifier, what is a linear classifier in RD? Can you bound the minimum possible non-responsive disclosure, or is it instance dependent? It's just that it's instance optimal.
So if you that's a very good question. So it's just instance optimal without making further assumptions.
So it could be unbounded.
It could be unbounded.
So even in R2.
Even in R2, we will see this in a few slides.
Okay.
And and then there was follow-up work by Dong, Hartline, Liren, and Vijayaraghavan, which sort of took the original TAR scheme, I think, of Grossman and Cormack, and replaced their manual labeling scheme with a verification protocol, which actually gave them empirical improvements. And for the verification protocol, they made it work in non-realizable settings, whereas the earlier protocols only worked in realizable settings. But it only worked when the data was one-dimensional, and it got a high recall. The recall was just shy of 1 by the error of the best classifier. So in other words, what they were suggesting is that the part in the TAR scheme where you take an SVM projection and ask for the top end documents to be manually reviewed, you instead use their protocol, because that kind of makes Alice accountable. It's not on her legal team to just declare which are responsible. So this is what, there are more results of course, but I think in a big picture view, this is what happened in the past 2 papers. And in this work, we sort of try to develop this critical points protocol to work for a general hypothesis class in both the realizable and non-realizable settings. And we achieve a recall of, again, 1 minus error star, where error star is the error of the optimal classifier in H if the setting is non-realizable. And we bound the non-responsive disclosure. So for the general hypothesis class, this is the question that he was asking, that how many points are revealed if Alice is truthful. Like for d equal to 1, we saw just a single point is revealed. But what if the setting is non-realizable or it's high dimensional data? Then we introduce a combinatorial measure of H, which we call the leave one out dimension, which captures the number of points that are revealed if Alice behaves truthfully, in the sense of the non-responsive disclosure. So the number of non-responsive points.
Good, so you get it basically. So it does depend on the hypothesis class, not on specific hypothesis. So for hypothesis of linear separators in RD, is it just D or is it bigger than that?
So so if you are taking all linear separators in RD, it's unbounded. or it's as large as the universe on which you're working, so mod S.
Okay.
But we will see, like, if you assume some margin criteria, you can get interesting problems. That's what we will see. But the first point was to develop a protocol which works for a general hypothesis class. And yeah, it can be efficient for certain settings. Yeah, this is what Nari was talking about. We get an interesting trichotomy of this dimension with respect to the margin of the linear classifiers, which we will see towards the end of the talk. And we also develop protocols which have another interesting property that if Alice makes an inadvertent error, we don't have an all or nothing mechanism. That is, like earlier we saw that when Alice makes even a single error, Bob reveals or Bob gets to learn all the points. But now we sort of do that in a more gradual, gentle way because errors are going to come up. Okay. But in this talk, we will only look at the realizable setting and we won't also bother about this point. So let's try to now jump into the protocol for the general hypothesis class because things are cleaner here and it's actually not very difficult to describe the protocol. So again, just to recall, we have this instance S which has been split into truly responsive and the non-responsive documents, and we assume that it's realizable with respect to some hypothesis class H, and Alice reveals all the documents S to Trent along with an LS responsive subset A+. So we might as well assume that Alice, the set that Alice reveals is contained in S+, because Alice has no incentive to take a negative document, a non-responsive document, and call it responsive. Even if she does do that, Trent can always just ask Bob. And if Bob says a responsive document is non-responsive, Trent can just call it non-responsive. The side which is worrying is the other one. That is, if Alice is trying to hide a responsive document as non-responsive. So we might always assume this happens. And then this is the protocol. So Trent computes critical points, whatever. So the first part or the outer protocol is kind of a copy of what we did in D equal to 1. So Trent computes the critical points, which we will define shortly. According to this LS responsive subset he has received from Alice. And then Trent will reveal all the points which are claimed as responsive by Alice and the critical points to Bob. And Trent verifies with Bob whether all points are non-responsive in CA plus in the set of critical points, resolving any conflicts in code. If all points are classified as non-responsive, then the protocol stops. And otherwise, Trent just reveals all documents to Bob. It's almost verbatim what we did for D equal to 1, except that critical points are now somewhat strange. So, what are the critical points for a general hypothesis?
So I guess just maybe getting to know. So for instance, if let's say 2 dimensions, points around the circle, exactly 1 is relevant, responsive analysis, nothing is responsive. There's no.
This is exactly the example I'll show. But yeah, you're right. That is the reason why you can't just bound it straightforwardly. Yeah. So what are the inputs again for the critical points protocol? The inputs are just points in RD. And there is a subset of points A plus which are claimed as responsive by Alice, and then we also have an oracle O which checks membership in the hypothesis class H. And what will be our output? Our output will be some subset of the negative points which we'll call critical. So what do we do here? So we start with all the negative points as candidates. So they can all plausibly participate in the set of critical points. For each candidate point, we'll check the following things. So if we try to label it, by V I mean Trent. Trent is the party computing this. If Trent tries to flip the label of this negative point to positive, while keeping all the other labels fixed, right? And this causes an invalid labeling. So this labeling does not belong to the hypothesis class H. Then Trent will just remove it. So Trent will remove that point. So maybe I should draw a picture here. So you have some bunch of points. So maybe these are all the points that are claimed as positive by Alice, and these are all the points which are labeled as negative. So Trent goes to each point and tries to flip the label from negative to positive and checks whether this new label that he has sort of new hypothesis that he has created, is that in script H? If it is, then he retains this point, he adds it to CA plus. If it is not, he just deletes this point. Okay? And this deletion is important. And eventually when the protocol runs through all the points, all the negative points, whatever you have collected are the set of critical points. So it's a very simple protocol. And
sorry, it's stated here as a sequential process. Is this important, or can I check this for each point separately?
no, it's important to keep it sequential. So if it is linear, then you can do it for each point in parallel. But if it is not linear, then you must do it sequential.
So CA plus there could be many valid possible CA pluses depending on the order in which you go over them.
Yes. Depending on what ordering of the points you have, you can get many different critical point sets. And this deletion, because you remove it once you process a thing, is what changes the critical set you will obtain.
What's an example where it can depend? Okay, maybe, sorry, I'll try to think through it.
Yeah, so here, if this point, so maybe this is the first point we process and we are not able to flip its label, so we delete the point, and the second point we process, we are able to flip its label, so this gets added into the critical set. And then you keep going. So you don't delete this point stays. Then you go to the next point, and so on. And with that, okay, let's just now try to understand what the properties of a protocol are. So the first thing to notice is that the protocol has a recall of 1. Okay. Let's see. So there are two possibilities. Either Alice has honestly revealed all the relevant documents. If that happens, there is no question because we always reveal A plus to Bob. So, but A plus is S plus in this situation, the ground truth. Okay. And if Alice is dishonest, then the point is that one of the critical points that you have revealed will actually be responsive. And hence Bob will learn all of S by our scheme, right? Because even if we check, or even if we figure out that Alice has cheated on one of the points, we will reveal everything to Bob. That is what we plan to do. So why is this the case? It's actually not very difficult. So suppose, in this set, there were some other points which were truly positive. So these points were actually the positive points. And then all the remaining points, all the other points were negative. At some point, your protocol it cannot be the case that all these points are missed by the critical point set. Because just imagine what happens if all these points get missed by the critical point set and you process the last of these points. So all these points are getting deleted. And then this point, you will wonder, okay, if I change its label from minus to plus, is that in my hypothesis class, right? But of course it is in your hypothesis class because this is a valid, this is the ground truth. S plus is A plus union this set. So because of that reason and because of the fact that we keep deleting when we when we are not able to flip the label, we will catch Alice if she is cheating. And what is the non-responsive disclosure? So the non-responsive disclosure of this, I would claim, is the leave one out dimension of the hypothesis. What is the leave one out dimension? The leave one out dimension is just the largest size of a subset of documents where you can isolate every document on its own. So for every document little c in capital C, there is some hypothesis which classifies little c as positive, but all the other documents as negative. This is very closely related to the star number which was introduced by Hinek and Yang. It's in fact a watered down version of what they introduced. but this is what the non-responsive disclosure will be. And that is actually not, again, that's not difficult to see, because whatever the set of critical points you end up with, so let's say that you selected some subset of points which are your critical points, and you pick up one of these points. The fact that it's a critical point means that you were able to label this as positive while everything else was being labeled as negative. And in fact, you had more. You were also able to label all of the alleged positive documents as positive. But what is important is just the behavior of the hypothesis class on the critical point set. It was able to isolate every point. That's why you added it to the critical point set in the first place. So this is not very difficult to see that the non-responsive disclosure is exactly the leave one out dimension of the hypothesis class. So this is, I'm probably not saying it very well, but if you just unpack the definitions, this comes out. And now one can ask, okay, what is the leave one out dimension of linear classifiers, right? Now that we have a combinatorial measure, we want to understand how does it behave with respect to the most basic classifier family with set of linear classifiers. Right? So let's say script H is the set of all linear classifiers on your set S, so on the set of documents S. So anything which can be separated by a hyperplane. And as Natty and Evrim both were saying, so suppose we take S to be n points on a circle. Right? So just imagine all the points are in R2 on a circle. You can see that the leave one out dimension is n, because you can isolate every point by choosing a chord close enough to that point. Right? So it's not quite interesting, because we would like bounds which do not depend on mod S at least. It depends on some parameters of the hypothesis class script H. Ideally, we would also not want it to depend on the dimension, the ambient dimension. So what if we consider a more robust notion of separation? That is, script H consists of classifiers which have some margin. Okay, so they don't only separate points, they separate it with some margin. Then what can the leave one out dimension grow unbounded? Right, that's the question. So we'll work with a notion of angle margin. So it's kind of like you project all your points to a hypersphere and then measure the angle that they are forming. This is, not super uncommon to do in learning, but for simplicity, we'll consider only classifiers which pass through the origin. You can always add an extra bias term, although one has to be careful because not everything is translationally invariant here. But nevertheless, angle margin by itself is a very interesting quantity. So we will study what happens if we are given that the set of hypotheses actually separates these points pretty well in sense of the angle margin. So the angle margin again is actually, I think, the cos inverse of this, because it's the angle, but it doesn't matter. We can just work with this definition. So what is H sub gamma? It is the set of all classifiers, all linear classifiers, which give an angle margin of at least gamma on the set S. So collect all such linear classifiers which have this large angle margin and look at the labels they produce. And we are trying to bound the leave one out dimension. So we are trying to bound how well can they isolate a set of points, provided that they have to do so with large angle margin. Now it turns out that this thing is actually related to a very classical geometric packing lemma, of which we are studying a skew version. Okay. So once again, we have a subset of points S in RD, and we are trying to figure out its leave one out dimension. We are trying to figure out the leave one out dimension of H sub gamma. Okay. I didn't have coffee today, that's why I'm fumbling so much, but we are trying to bound this. We want to say this is not too large, because that would help us bound the non-responsive disclosure. So suppose this size is k. What does that mean? That means that there is a subset of points of size k such that every point in that subset can be isolated by some linear classifier HC. right? So every point little c can be isolated by some linear classifier HC. And we might as well assume, since we are working with an angle margin constraint, we might as well assume that C is unit and the linear classifier which is separating C is also unit. Okay. This doesn't matter because the angle anyways normalizes all these points. So because of the margin constraints, because of the margin conditions, we have the following interesting set of equations. That is the inner product of WC and C. So what is WC? WC is the sort of normal vector for the hyperplane which is isolating C. Okay. So the inner product of WC and C is greater than or equal to gamma, because gamma was our margin. Gamma was our assumed angle margin. And for the other points, they are actually labeled as -1. That means their inner product would be minus gamma. The inner product of WC and C prime would be at most minus gamma, right? If C prime is not C, because it is supposed to classify C prime as -1. That means it's giving a negative value, but also it is supposed to do so with a large angle margin. So those two things force this condition, and so this becomes like a skew obtuse packing of vectors, right? And unless I have not lost you, this is I think a very good point to wake up again and come back to the talk, because what I'm going to talk about from this point is independent of what has happened so far, because this is a very clean geometric question to answer. So you have a, yes?
Is this dimension always smaller than the star number?
For, yes, yes.
This is because it's non-symmetrical, the positive and negatives. That's the reason it's smaller.
I somehow like, okay, I'm not very sure, but I think their star number has 2 parameters, if I'm not wrong, and somehow we thought that this leave one out dimension is just an instantiation of one of those parameters. So yeah, I think there's star number definition, if I'm not wrong, is a little more complicated. Like you have to also be able to isolate all sets of points up to cardinality R. So yeah. Okay, so once again you have a bunch of yes, 10 minutes. Okay, so yeah, we have a bunch of unit vectors. Usually we talk about obtuse packing. That is, we want a bunch of vectors in RD which are sort of at obtuse angles with each other mutually. But here now you have a skew condition. So for every C there is a vector WC which is close to it but far away from any other C prime. So obtuse packing is very classically studied everywhere, and I mean it's used in coding theory and at many other places. And obtuse families would just require WC to be C, right? So you have just a bunch of mutually obtuse vectors, and how many of them can you pack in RD is the question. If I force the angles to be small, a fixed constant more than 90 degrees. So that's the condition that the inner product is less than minus gamma, and classical bounds say that this is at most order 1 over gamma. And skew properties are also very classically studied. Like this idea of having 2 families and looking at the crosswise properties is very classically studied in combinatorics. And like there are famous theorems due to Polavash, Loash, and Furedi studying these things. So we are in some sense merging these two. We are studying the skew properties of obtuse packing. And they can also be interpreted as giving distance bounds. I mean, this is some coding theory stuff. It's not very relevant for the talk right now, but they can also be used to give Plotkin-like bounds on skew codes. So how do we obtain bounds on the skew obtuse packing? Okay, so here's where the thing becomes a little challenging. So let's think that V is the. So I'm just going to draw this here. So V is this matrix where we are just stacking the points C. So let's say that our set of the witnessing set C, which we are claiming is actually I don't need that. So let's just say that our skew obtuse family consists of the vectors C1 up to Ck and WC1, WC2 up to WCK. Maybe that's bad notation, but V is the matrix which is just stacking all the C vectors row wise, and W is the matrix which is just stacking all the column vectors all the W vectors rho 1. That's all. Now, if we do VW transpose, if you just do the matrix multiplication VW transpose, on the diagonals you will just get Ci inner WCI or C inner WC. So each of the diagonals will be greater than equal to gamma because that's the skew packing constraint. And all the off diagonal entries will be below minus gamma because that's again the skew packing constraint, right? So if we were just doing obtuse packing, the proof is very short from here. Right? If we were doing obtuse packing, then we would just say V equals W, and we would say that VW transpose is PSD because W is V, and then it's just a matter of analyzing the sum of entries of this matrix. So VW transpose is a matrix where all the diagonals would be 1 if V equals W, and all the off diagonal entries will be below minus gamma. And if you do the sum of all the entries, it is at most k, that is the sum of the diagonals, and then the minus gamma that you are accounting for on the off diagonal entries. But on the other hand, this sum has to be positive. So if you just rearrange these numbers, you get the desired count. And this is what is very sort of a classical proof of this fact. But for skew obtuse packing, the problem is this matrix isn't PSD, right? Because V and W need not be the same vectors. And you can sort of try to embed that into a PSD matrix, but then it doesn't give tight bounds. So we have to do something different. And what we instead do is that we bound this quantity, which is, so what is AI? AI is just the column vectors in this matrix P. So this is AI, and this would be, these are all K cross D matrices because we have D-dimensional vectors, and this is BI. And what we are looking at is this quantity, which somehow turns out to be very interesting in bounding the size of skew obtuse family of vectors. It is the product of the column norms summed. So just by Cauchy-Schwarz, you know it is at most k because 5 minutes. Okay, I'll wait. So just by Cauchy-Schwarz, we know it is at most k because if you just use Cauchy-Schwarz, you get this kind of nice expression, which is just the sum or square of entries of each matrix. And since this is just the Frobenius norm, so you get that this is k. It's not. And now comes the interesting part, that there is another. So we need an upper bound on this quantity. So we have a lower bound. We need an upper bound. Sorry, we have an upper bound. Now we need a lower bound. So let's say theta I is the angle between AI and BI. So AI and BI are the two column vectors. And so this is the picture. So you have, this is BI, this is BI, and this is theta I. And we'll come to alpha I and beta I later, but these are the angles between 1 and minus AI and 1 and BI. That's all. So just be sure this angle will actually turn out to be more than 90 degrees. So this is a better picture to keep in mind. So this is minus AI. And now it turns out that we can write summation AI bi cos theta I as just the trace of W. Because this is just a simple computation. And because this we know is at least k gamma, because these are just the diagonal entries of VW transpose which are all promised to be more than gamma. But interestingly, the other part which will finally give us the sum AI dot BI can be obtained by looking at the sum of entries of VW transpose, which we did anyways, but through a somewhat interesting lens. So it's, for technical reasons, better to just work with the minus of the sum of entries. And if you just follow this algebra through, it turns out to be something like this. It's not very important. The algebra is not very important. But what is important here is that you get this cos alpha I, cos beta I in product. Alpha I is the angle between all ones and minus AI, and beta I is the angle between 1 and BI, right? And now, when can this product be maximum? So it's just using this simple fact that if you want the product between a third vector to be the product of the cosines of the angles between a third vector with bi and ai to minus ai to be maximum, the best thing you can do is choose the angle which bisects ai and bi. Right? This is a very simple geometric fact. So if you kind of use that, you will get that cos alpha I, cos beta I is at most the cosine, like assuming that it bisects is at most this expression, which nicely turns out to be able to kill this extra cos theta I term that we have here if we multiply by it 2. And on the other hand, we also know that the sum of entries is not, the negative sum of entries is not too small because the off diagonal entries are all minus gamma. So if you kind of plug these equations all together, you are able to show this interesting trichotomy that if the angle margin is greater than 1/3, then any skew obtuse family has size at most order 1 over gamma. Okay, this is the correct expression, but it doesn't depend on the dimension. And this is tight because as soon as you put gamma to be 1/3, you can construct a family which has d points, and if gamma is less than 1/3, this greater than 1/3 is wrong. This should have been less than 1/3. If the angle margin is too small, you can actually pack in exponentially many points which satisfy the skew obtuse constraint. This is in contrast to what happens in the obtuse setting where gamma equal to 0 is the straight cutoff. Like if gamma is greater than 0, you can pack in exponentially many vectors. If gamma is 0, you can pack in linearly many vectors. And if gamma is less than 0, then you can only pack in order 1 over gamma vectors. Okay, so this is I thought somewhat of an interesting result, extension of the usual geometric packing that we do. But that's it.
Wait, I'm sorry. That should be less than 1/3?
Yeah. This is a typo. This should be
Okay,
less.
okay.
Sorry. Yeah. So I think I'm also out of time. So we have some further directions where we can try to use some distributional assumptions to see these commutative dimensions for more complicated classes. Because trying to bound it for general classes will be very difficult. So we are trying to see what are reasonable assumptions. And whatever you suggest will also be helpful.
Questions? Right? Oh, sorry.
So, can you say again why leave one out dimension is the lower bound for NRT?
Yes, so if Alice behaves truthfully, we are only revealing the set of critical points, and we are sort of in the setting where we are assuming everything is realizable. Now, so we want to say that the set of critical points actually are such that every point in this can be isolated by your hypothesis class. So pick any point you want. What we are trying to see is if the following labeling, where this point is positive, the point that you have picked, and every other point is negative, is that in your hypothesis class? Well, it is, because why did you add this point in your critical set? Whenever you added this point, every other point was either not processed or it survived, and then you can clearly see it has it.
So is this I'm curious, the lower bound, you show the lower bound on the leave one out dimension. Does that translate to a lower bound on in the retrieval problem? Like
Yes, they are exactly
the
related.
exact match. Okay.
Yes. Yeah, exactly.
So you said there is a trichotomy. For gamma equals 0, it's linear, then it's exponential, then it's the other term. The first one is linear in what? In the number of samples?
Oh, this one? Oh, this is in the dimension. So you are talking. This is a question about like how many skew, like what's the largest size of a skew obtuse family I can have in RD.
So if gamma equals 0, you get something linear in the dimension?
No, if gamma is 1/3, we get something that is linear in the dimension.
Then because you get exponential dimension.
Okay, that makes sense.
Okay, so let's thanks Sven again. That's it for theory talks for the quarter. We'll be back next year. Next week we're gonna have Matthew Turk speaking to us.
Now we'll have Luja present his work as part of the student workshop.
Oh, I wasn't regulating.
Oh, no, I'm just asking, like, they
all finished within 15
Marcelo, care about negative relations and positive. If you
Nobody needed
just
stuff.
would care about change of sign, that's exactly.
Are you timing the talks or am
I
I?
think it's one way or
We
like
haven't needed
non-symmetric
Oh, I see, I
sign or
see.
something.
Okay, I see.
but yeah,
But you will be here.
yeah.
See that? I think that this is like exactly the star number, but a non-symmetric version. Like if you care about minuses, the very good classes, right? If you just would care about the change of signs, you would think it's exactly the same.
So, yeah,
Yeah,
I
for
think
us,
I mean, what it was star number with
This is the star number. Points such that you can
It's alright.
isolate. This is the function.
Well, it's not.
there is some hypothesis such that HIXJ is HXJ, so except for that one,
Change
you
your
agree on
mind.
the sign.
No, because Karen
H1 is like
Karen
quantized
find
center.
calling my name pretty difficult. And she wants to
Oh, I see.
Except one point.
Except that I.
So like there is this function and then
Yeah.
Hello everyone, today I'm going to talk about my recent work, Flashback, consistent model of accelerated shared autonomy. Below are two images. First is for the packet insertion, the second is for the charging insertion. And first thing, what is shared autonomy? Look at the big vehicle on the right. It's a underwater, like ocean exploring machine. You can do it by remote teleoperation or fully autonomy. And it can travel at the depth of 2,000 meters. And it can travel 40 kilometers per day. And it can connect the signal by the hair-thin fiber. But there are some requirement limitations for this big machine. First is to run it for 1 day, it will take over $50,000. And the time to train the staff and the scientists to work on this ship usually take months and years. And their space limit, the ship is not as big as you think, so it will limit the participation numbers. And we were thinking about whether we can find something in the middle between the fully teleoperation or the fully autonomy. Whether we can let a user share the control with the robot assistant agent for some very hard operation tasks. Previous work always assumed that we can know the user's goal or we can infer the user's goal before executing, which means you can find some clue that the goal is discrete and finite. But what if the user changes their mind, say, now I don't want to go to the green object, now I want to change it to the cube? What if the goal is unknown, is unpredictable and continuous? Can we still do the shared autonomy? One methodology we can think is the diffusion model. Diffusion model don't care about whether you're under the water, whether you are training with a robot or training with an image. All you need to provide to the diffusion model is the demonstrations, because it's a model-free generating framework. This is our previous work to the noise and back. First, we collect some the expert demonstrations, and we train a diffusion model as it is. We forward add noise and we denoise to get this trajectory. And during inference time, when a user action comes, it's a totally new distribution that the diffusion model have never seen. What we are applying here is called a partial diffusion, which means you add some amount of noise until you reach some point that a diffusion model cannot tell whether this distribution is learned or not. Just this distribution look very like this one. So you can cheat the diffusion model, say you have learned this distribution before. We call this partial diffusion. You add a little bit of noise, then you denoise. But there are some limitations about this previous method. we are working on the simulation tasks like lunar reacher, lunar lander, block push-in, or the UR5 ring toss. All of these tasks are very naive. The action space is just 2, which means it's a 2D operation task. Whether our model still work on some high dimensional and a high precision task, this is unknown to us. To work on the high dimensional task, you need to guarantee your inference speed, which means if you want to do the real-time assistance, your inference speed need to be very high. And when the diffusion model have such a capability to deal with a high precision task is still another unknown thing for us. Another related work called DexGen. Obviously, this robot hand is much complex than the 2D thing. It has 16 degrees of freedom to operate on this very complex task like a screw, like drawing something. What they are doing is they collect data in the simulation environment, and then they train the diffusion model just as it is. But during the inference time, they're doing a simulation to reality transfer, and they accept a user motion. Then they add a punishment on the diffusion model inference time, which means when your generative action is far away from the original action that the user input, it will get a punishment. So they call this motion guidance diffusion model. But what their limitations is here. They call the foundation controller. Why they're doing this simulation to reality transfer? Why they don't directly train on the reality data? Because they require 10 to the 10 amount of data. You probably don't have a sense how much this data means. In their paper, they reported to train a single task, they will take 96 GPU for 3 days, just for one task. So this is the limitation for this foundation model. So based on all the limitation I talked before, we proposed our model, consistent model accelerated shared autonomy, CSA. We can guarantee the fast inference time, and we are doing uniformly training, which means no matter what the task looks like, we never change the model. We never change the hyperparameter. You always use the same hyperparameter for different tasks. And we tested it can work with relatively small data set, which means you don't have to take a GPU for 3 days or something. And we can do the high precision task, just like the charge insertion. The last thing is about the border, the sweet spot, I'll explain later. I'll go through all these concepts one by one. So if you have questions, you can ask later. So for some preliminary, the DDPM model, we all see this as a add noise and denoise. We learn a score function and we follow the score function to do some denoising step, just like this noisy dog. We predict the noise at this image, we denoise, and we do this iteratively until we get a clean sample. But the question here is the iterative step take a long time. Usually it's like 100 step or even more. The question here is, can we do like the one-step collapse, like jump from here directly to here? Another not a very good thing for our task is DDPM is solving a stochastic differential equation, which means for the numerical solver, they will introduce a fresh noise at each step. This may guide you from your original path to another related close path, and hence we will get into another dog, which is the nearest dog that you want. The question here, as I said, the question here is, can we do the one-step denoising and guarantee you can find your nearest neighbor? The answer is yes. Let's see this 2D example. I marked all these samples by the color to their nearest neighbor. For the original DDPM, for the naive DDPM model, which uses the SDE, which is stochastic differential equation, you can see the red dot go to the blue target, the blue one go to the green. There's some mixing here, which means you cannot guarantee you find your nearest neighbor. But for the consistent model, you can find your nearest neighbor within one step, just one jump. But how? How we achieve this? We are training the model, start from some expert data, like I said, expert demonstrations. We add noise until you get the pure Gaussian noise. Then we first train a teacher model. The teacher model is an ODE-based diffusion model. here ODE is an ordinary differential equation. And you can use DDPM, DDIM, EDM, no matter which type of diffusion model you choose. What you are doing is like previously, you do the one-step denoise from AT to AT minus 1 or from AN to AN minus 1. And the only difference here is when you are using the ODE model, your denoising trajectory is deterministic, which means given a specific noise, apply this model, you will always guarantee to get the same sample. The path is deterministic. After we train the teacher model, what we are doing is we train a student model to distill the knowledge from the teacher. How to distill? We start from different points on this path, and we do this one-step mapping to get the clean sample. And we minimize all the clean samples that the student model provided from different start points. Hence, we can distill the knowledge from the teacher model. This is a one-step jump. During inference time, we just assume the user's action is like some point along this trajectory, say AK. And then we directly apply the student model to do this one-step denoising, and we can get the clean sample. This is a fast inference that I mentioned. Now you don't do one iteratively reverse step, you're doing the one-step jump. And for our task, we're doing this 4 different experiments from easy to hard. This is also the 2D lunar lander. You operate the vehicle to land on the space landing pad, and you do the pack insertion to the socket, and you have the charge insertion and the real robot thing. First is uniformly training. As I said, from easy to hard, we always apply the same model and the same hyperparameter. We don't need to tune anything. Second, we can work with small data set. For all these tasks, simulation tasks, we are all working with 200K training data. Last thing, high precision. For this high dimension, high precision. For this pack insertion, the state dimension is 35, action dimension 8. And for this charge plug, it's for the high precision, it's like industrial level clearance. The clearance is just 0.5 millimeter. Let's see the result. Originally, you can see the surrogate almost fail all the time, that it doesn't know, it's shaking a lot. Even for this 1 centimeter clearance, you cannot fit the pack in. And for the DDPM model, you can see for the relatively easy pack insertion task, it succeeds sometimes. It can still assist the surrogate in some sense. But for this high precision task, DDPM cannot converge with this amount of data. For our CSA model, the pack insertion, it almost succeeds every time. I believe the statistic result is 80% or something. It fails for some trajectory. And for this charge insertion, as I said, very challenging. For the 3, I'm not cherry picking. For the 3 episodes, it succeed twice, and the statistic result will be 70% high, I believe. Yeah. This is impressive. And get back to the last concept that I mentioned for the border, the sweet spot. For both previous work and current work, we are always mentioned one of the hyperparameter K. This K control how many amount of noise that you think the current user action contains. And this K has a trade-off between whether you are fully respected user, but you are not very professional, or you are very professional just like an expert, but you don't know where the goal is. You are doing some meaningless expert action. But can we make this K not that sensitive? So we propose the forward model to border the sweet spot. The forward model is very straightforward. It's just guess what's the current user's intention is. Given the current state and action, what's the next state would be. Previously, at this point, you will have many modalities that you can choose, but with our forward model, you can see that it will predict, okay, probably the user have a high probability will falling into this narrow distribution. And we believe with the forward model, we will never use the user's intention, like the fidelity never goes down that much, and hence we can keep the performance always at a very high level. This is what I mean by border the sweet spot. And if you see the static result is actually aligned with our assumption. After